All right, I got 8:30. Let's go ahead and get started. Morning, welcome. So a couple warm-up questions here for you to think about for a minute. A lot of stuff to get through today. I want to make sure we finish everything that you need before quiz 7, which will open this weekend. So we'll see how things go. I might end up skipping our normal short break in the middle. If that happens, I apologize, but just want to make sure we get to everything, and I don't want to rush through anything, so try and make sure that we see some good math today. Okay, so starting with a warm-up question. Last time we talked about chromatic number, so we talked about vertex colorings, proper vertex colorings. Each vertex gets its own color, and two vertices that are adjacent should not share a color. And then we can always do that, right? We could always give each vertex its own unique color. That would work for sure. But if we only have one color, that's not going to be enough if there's any edges. So the question is, what's the smallest number of colors required? And that was called our chromatic number. And we used chi, Greek letter chi, for chromatic number. So, start us off. What is the chromatic number of K and M? If I've got a bunch of vertices over here, a bunch of vertices over here, I have all the different edges between them. How many colors does it take? Yeah, really good. Only takes two colors, right? I can make all of these blue. And I can make all of these over here green. And there's no problems, because the edges only go across from one side to the other. So this is a bipartite graph, right? This is a complete bipartite graph. And what we notice is that we can always do this with a bipartite graph. Right, I can always put all the blue vertices on one side and all the green vertices on another side, and then the edges will just all go across. Doesn't even matter what N and M are. Doesn't matter how many I have here. These will all be blue, these will all be green. So I can always get two. Really nice. Slightly harder one. How about this chromatic number of k-dimensional hypergraph? UK. So here, remember, I've got a vertex for every string of zeros and ones. And if I have something like 1, 0, 1, 1, 0, 1, that'll be adjacent to 0, 0, 1, 1, 0, 1, to 1, 1, 1, 1, 0, 1, to 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, and 1, 0, 1, 1, 0, 0. This is a tricky one. I want to give you a minute to think about it. Then I'm going to tell you the answer, and I'm going to see if you can figure out why. Any guesses? It's okay if you're wrong. What are some things that it could be that seem reasonable? K, 2 to the K. So 2 to the K, definitely a reasonable guess, right? We have 2 to the K vertices, 2 to the K colors. Seems perfectly reasonable. K also seems perfectly reasonable, right? If I have like a different color, or maybe even K plus 1, if I've got like a different color for everybody around me, those all seem reasonable. K is like, K makes sense because there's like a K here, but when we actually look at this picture, K would be a little weird, right? Because that would mean like two of these share a color, because I've got K plus 1 vertices in this picture. Okay, so now I'm going to tell you the answer. And then I want you to think again, is there any way we can figure out why that's the answer? So the answer is actually also 2. Doesn't matter how many dimensions, only need 2 colors. So now I want you to think about why that could be. What argument could we use? What picture are we going for? Center one color, everything else is another. Okay. So let's build on this idea. So let me make this one red. And then everything else green. But of course, this isn't the whole graph, right? It's going to keep going. So each one of these green vertices is now the center of its own little picture. And those are all going to be red. And what I want to make sure is I want to make sure that there's no looping back around. Right? It would be bad if I had a picture that looked like this. Then this is in the center of something, so this one should be red. And this is in the center of something, so this should be red, but then I have that problem of 2 reds right next to each other. So how can I be sure that that doesn't happen? Well, let me draw you another picture. The only way that this is going to work is if I can remember, graphs are not pictures. So I can rearrange this graph, I can move things around. And if I'm allowed to only use 2 colors, it must be the case that I can put all the red vertices over here, and there's no edges inside this blob. And I can put all the green edges over here, and there's no edges inside this blob. And I might not have every edge, right? This is not a complete graph, but all of the edges go from one side to the other. No edges stay inside. So if I wanted to rearrange my graph and make it look like this, I would need to prove that. I would need to explain which vertices go on this side and which vertices go on this side. Can you see any way to split up the vertices in my hypercube? I'll give you a hint. These labels are chosen. There's something about these labels. Something's going to be a red label and something's going to be a green label. What properties might a binary string have? Okay, really good idea. I like this a lot. Half of my vertices start with 1, half start with 0. Only one problem though. These 2 strings both start with 1, and they have different colors because they're adjacent to each other. So start with 1, start with 0, really good idea. Just doesn't quite work out, but let's build on that. What property do I know these strings have? Do binary strings have? It's a trickier one. First digit isn't quite the right idea, but it's on the right path. What are some other properties that binary strings can have, even if they don't work? Let's just talk about properties of binary strings. Maybe let's look at another vertex in our hypercube. There are 2 to the k possible strings, right? So let's look at the vertex 0, 0, 0, 0, 0, 0. This is off somewhere else in the graph. Turns out it's going to be red. I know that ahead of time. So that's a hint. And then this is going to be adjacent to 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1. And each of these are going to end up being green. There we go. Very nice. Very pleased. The number of bits that are 1, whether that number is even or odd, is called the parity of the binary string. And what we notice, because there's an edge from a vertex to another vertex by flipping 1 bit, every edge changes parity. So these are all the even parities, even number of 1s, and these are all the odd parities, odd number of 1s. And every edge is between a vertex with an even number of 1s and an odd number of 1s, because I always change them one at a time. So because I only change 1 digit at a time, I'm always guaranteed to have the structure, which means I can color all of the vertices with an even number of bits red, and all of the vertices with an odd number of bits green, and I know there's no way for me to have an edge from red to red. There's no way for me to have an edge from green to green, because every edge changes parity, which is why 2 is enough. This is one of my favorite graph theory proofs, because this is exactly one of those where you stare at this problem and you're like, maybe I need 2 to the k colors. Maybe there's a clever way to get away with maybe just k colors. What? How can the answer be 2? How can it only be 2 colors? And then as soon as you see the explanation, you're like, that's clever. That's good. Now that I know it, I feel smart. Like I know how to make this explanation, and I know how to convince other people that it's only 2 colors. Okay. So I do want to expand on this a little bit and prove a theorem. And this theorem is a type of theorem we like in graph theory. It's a structural theorem. It tells us that a bunch of things are actually all the same thing. And it's the type of theorem we see a lot in mathematics. So theorem, the following conditions are all equivalent. So, a graph is bipartite, not complete bipartite, just bipartite. Meaning, I can break it up into these 2 parts and all the edges go across. I'm not guaranteed to have all the edges, just that there's no edges inside my blobs. The graph has chromatic number 2. And the graph has no odd cycles. And I'm going to prove this. And the way that we prove theorems that look like this, following conditions are all equivalent. Let me actually even put in labels here, A, B, and C. Is I'm going to prove, so the following conditions are all equivalent means A, if and only if B, if and only if C. But I don't want to have to prove 6 different directions. I don't want to have to prove A implies B, B implies A implies C, C implies A, B implies C, C implies A. That would be like doing 6 proofs. I can get away with only doing 3 proofs if I prove, so here's the idea, I'm going to prove that A implies B. I'm going to prove that B implies C. And I'm going to prove that C implies A. And then I get the opposite directions for free. I know A implies B because I proved it. I know B implies A because B implies C and C implies A. So I can use one of my laws of logic to get B implies A without proving it separately. So let me do these 3 proofs for you. Proof number 1, A implies B. If a graph is bipartite, then it has chromatic number 2. Well, I know my graph is bipartite, so G is bipartite with parts A and B. I'm going to color all the parts in A with color 1. Color all the vertices, sorry. A with color 1, all vertices in part B with color 2. There are no edges inside the parts. So this is a valid coloring. I guess I need a graph to have at least one edge. Otherwise, you could use one color, but that's sort of a silly example. So if G has at least one edge, then the following conditions are all equivalent. It's bipartite, it has chromatic number 2, it has no odd cycles. Okay, so that's A implies B. Assume bipartite, prove it has chromatic number 2. Step 2, prove B implies C. Assume it has chromatic number 2, show that it has no odd cycles. This one I can do by contradiction. So assume for sake of contradiction G has an odd cycle. We can look at the colors of that cycle in the 2 coloring. Let's say CK for some odd K. This gives a 2 coloring. This CK inherits a 2 coloring. From the 2 coloring of G. Right? I'm 2 coloring G and I'm just focusing in on my odds on my cycle here. But that's a contradiction because we know if K is odd, the chromatic number of CK is 3. We talked about this last time. Chromatic number of CK is 3 for odd K. So that's a contradiction. Close that in there. Okay, so one last proof to do. I need to prove that C implies A. If the graph has no odd cycles, then it is bipartite. Okay, and what I'm going to do is I'm going to build the partition. So while there are vertices remaining in G, so create 2 sets. A and B. While there are unlabeled vertices in G. Choose any vertex and label it A. Okay. Then label all of its neighbors B. Or, yeah, label one neighbor B. Label one of its neighbors B. Then label one of that vertice's neighbors A. And then continue this process until you reach a vertex with no unlabeled neighbors. Okay, so what am I doing? I'm picking out a cycle. I'm going A, B, A, B, A, B, A, B. Maybe I just get a path. That's fine. But it can't be the case that any vertex that's labeled B has a neighbor that's labeled A. I'm sorry, that's labeled B. And it can't be the vertex can't be the case that any vertex labeled B has a neighbor also labeled B. It also can't be the case that any vertex labeled A has a neighbor that's also A, because either of those would give an odd cycle. So no vertex labeled A has any neighbors labeled A. Similarly for B. And that's because G has no odd cycles. So therefore, when I run, I keep doing this until every vertex is labeled, and then every vertex is labeled, A and B form a partition, a bipartition. So this one's a little bit more involved than my other two proofs, but it's the same type of idea. And what I get are three conditions that all mean the same thing. Bipartite graphs are exactly the graphs with chromatic number 2 are exactly the graphs that have no odd cycles in them. Okay. Let me pause there. Questions about this theorem? So remember, we talked last class about how a bipartite graph can't have a triangle inside of it. But actually what we're saying here is your bipartite graph can't have any odd cycle in it. For that same reason of you bounce back and forth and then you end up with two vertices that would have to be in the same part, and that doesn't work. Okay. I want to talk about another type of graph. So a graph is acyclic if it contains no cycles. Okay. What's a quick theorem we get for absolutely free? If G is acyclic, what is the chromatic number of G? Two. Really good. If you have no cycles, a graph with no cycles has no odd cycles. Right? If you don't sell, I don't know, bottle caps at your store, then you don't sell this one super rare bottle cap because you don't sell any. That was a terrible example. If you have no cycles, then in particular you have no odd cycles. And we just said graphs without odd cycles have chromatic number 2. And a particular type of acyclic graph is a connected acyclic graph, which we call a tree. So I want you to just think a little bit about why that might be. Why would we call it a tree? Well, let's look at a graph without a cycle. I have some vertex. It has some neighbors. And then they have some neighbors. Maybe that one has one. Maybe this guy has a bunch. This guy maybe has a bunch as well. And then maybe some of them have neighbors. But I'm never allowed to loop back around. Once I start somewhere, I never complete a cycle. Each edge just leads me off into its own sub-branch. And so that's why we call these trees. It's connected, but there's no cycles going on. By the way, if we're just acyclic and not connected, an acyclic graph is called a forest. Because each part of the forest is a tree. Each connected component of the disconnected graph looks like this in some sense. It's a tree. So if I've got a bunch of trees, I have a forest. Okay. So we know a bunch of things about trees already. By definition, they are acyclic, which means we know they have chromatic number 2, which means we also know that they're bipartite. Right? That's the power of these structural theorems. We get, once we know one small fact about a graph, we get all of these other things for free. Okay, let's prove some theorems about trees. This up just a little bit more. Okay. So theorem. Every finite tree, which is really the only type of tree we're going to talk about in this class, but it's important for this theorem to be true, satisfies the number of vertices in the tree is one more than the number of edges in the tree. So let's look at this tree. Let's just make sure that that's true. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 vertices. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 edges. So 18 plus 1 is 19. So that checks out. Okay. What are we thinking? How should we prove a statement like this? We want it to be true for any size, any number of vertices. Yeah, really good. We want to prove this by induction. So we're going to prove this by induction. And our induction is going to be on the number of vertices in our tree. So I'm going to proof let P of n be the statement. A tree with n vertices has n minus 1 edges. And I should say for n greater than or equal to 1, let this statement be. Okay, what's my base case going to be? Good. And why is P of 1 true? It's just one vertex, right? It has 0 edges. P of 1 is true because the only graph, remember, our definition of a graph does not have loops. So the only graph on one vertex has 0 edges, and 1 is equal to 0 plus 1. Okay. So now I want my induction hypothesis. My induction hypothesis is going to be let k be greater than or equal to 1 and assume P of k. Now it's time for my induction step. And my induction step has a really important idea in it. What I have in my induction step is any tree. I need P of k plus 1 to be true, which means I have some tree that has k plus 1 vertices. I don't know anything about this tree. I need to prove something about it, and I want to use induction. So somehow I have to turn a tree with k plus 1 vertices into a tree with k vertices. And the easiest way to do that is to find a vertex that has degree 1. Because if I have a vertex with degree 1, that's one vertex and one edge. I eliminate those two. What I'm left with is a tree on k vertices. I know that's going to have this relationship. Then I add back one more vertex, one more edge. This will still be true. So what I need is that there exists a vertex with degree 1. Anyone know why I can always find a vertex with degree 1? We did talk about it, but it is tricky. We talked about it last class. Okay, in the interest of time, I'm going to spoil it. We know, or let me start with, let G be a tree on k plus 1 vertices. We know that the minimal degree of G is equal to 1 because if the minimal degree of G was greater than or equal to 2, I should say less than or equal to 1. If the minimal degree of G was greater than or equal to 2, we proved a theorem last time that this means G contains a cycle. Last time we proved minimal degree of G greater than or equal to 2 implies G contains a cycle, but G is a tree, so it has no cycle. Okay. Now we know the minimum degree of G is exactly 1 because G is a tree, so G is connected. So G has k plus 1 vertices. K is at least 1, so I have at least 2 vertices. You have at least 2 vertices and you're connected, that means your minimal degree is at least 1. Okay, so my minimal degree, well, I know it's less than or equal to 1 because it doesn't have a cycle. I know it's greater than or equal to 1 because it's connected. And so if you're both less than or equal to 1 and greater than or equal to 1, then you're equal to 1. So delta of G equals 1. And there exists a vertex V with degree of V equal to 1. I can definitely find a vertex that has degree 1. And now all I need to do is remove that vertex. Let G prime be the graph with the vertex set without the element V, and the edge set without the edge V comma W, where W was the neighbor of V. Okay. I know G had no cycles. That means G prime has no cycles. Since G prime is a subgraph of G, it also has no cycles. I also know it's connected. Since G was connected, and the degree of V was equal to 1, G prime is also connected. So G prime is a tree on k plus 1 minus 1 equals k vertices. By my induction hypothesis, G prime has k minus 1 edges. And now I'm ready to finish up. So G has k plus 1 vertices and k minus 1 plus 1 equals k edges. So therefore, p of k implies p of k plus 1, and for all n at least 1, p of n holds. That's the end of my proof. So we had this really key idea. I know I can't have a cycle, and if my minimal degree was always 2, I would have a cycle. So I have this vertex of degree 1. I have this leaf on my tree that I can pull off. And that is indeed what we call a vertex of degree 1 in a tree. So a vertex of degree 1 in a tree is called a leaf. So I always can find at least one leaf, because if not, then I would have a cycle. But actually, every tree on at least 2 vertices has at least 2 leaves. So I'm not going to prove this one in the interest of time, but you can sort of see how it would make sense. I start with a vertex. As soon as I add another vertex, I have 2 leaves. And then when I add another vertex, one stops being a leaf, but I always get a new leaf. Anytime I add a vertex to the end of something, because I can't complete a cycle, I'm always getting a new leaf. Okay. And so the one thing I will prove, the last thing I will prove about trees, is another structural theorem. So theorem. The following conditions are equivalent. G is a tree. For every pair of distinct vertices U and V in the vertex set of G, there's a unique path from U to V. C, G is connected and the number of vertices is the number of edges plus 1. And D, G is acyclic. And the number of vertices is equal to the number of edges plus 1. So that's my theorem. Any one of these 4 conditions implies all the rest. And I definitely do not want to prove A implies B, B implies A implies C, C implies A implies D, D implies A, B implies C, C implies B. All of those. That's way too many. There are 4 times 3, that would be 12 different things to prove. I only want to prove 4 of them. So I'm going to prove A implies B, B implies C, C implies D, D implies A. So let's do that. So proof part 1, A implies B. So G is a tree, which means it is connected and acyclic. So since G is connected, that means that this path must exist. Right? If there was no path, then G wouldn't be connected. And now we can assume for the sake of contradiction that there are two paths. That produces a cycle. And I'll draw a picture to explain why. So I have U, and I have V, and I have one path like that, and I have another path like this. And if I put those two paths together, I'm getting a cycle. But since I'm in a tree, I don't have a cycle. So if I'm a tree, meaning if I'm connected and acyclic, then I have this distinct path between every pair of vertices. Unique path between every pair of distinct vertices. Okay. That's one. Shame that I can't keep everything up on the screen at the same time. B implies C. So I have these distinct vertices. I have this distinct path, unique paths between distinct vertices, unique paths. I want to prove that I'm connected and that my number of edges plus 1 is equal to my number of vertices. So because these paths exist, I'm connected. So I get connected relatively for free. And now I need to show my number of vertices is equal to my number of edges plus 1, given that these paths are unique. Because I know I'm connected, if I can prove I'm acyclic, then I know from this last theorem that I proved that I'm a tree, and therefore I have the right number of vertices and edges. So G is connected, G is acyclic, because otherwise there would be two paths. The path between vertices on the cycle would not be unique. So G is a tree. And therefore, number of vertices is equal to number of edges plus 1 by that theorem I just proved. Okay. Next, I need C implies D. So C implies D. I already have the correct number of vertices. I just need to show if I have the correct number of vertices and edges and I'm connected, then I must be acyclic. So if I assume for the sake of contradiction that G contains a cycle, then that cycle has the same number of edges and vertices. And if I look at the remaining vertices and edges, there's just not enough to be connected. So that cycle contains k vertices and k edges. I have these k vertices and k edges. That means there are size of v minus k other vertices, each of which is adjacent to some other vertex. Eventually connecting back to the cycle. So what I'm really doing is counting paths back to the cycle, but some other vertex eventually leading to the cycle. Which requires that number of vertices minus k edges. Right, so if I'm going to connect all of these vertices back to the cycle, I need an edge either to connect that vertex to the cycle directly or to connect that vertex to a vertex that's connected to the cycle. Anytime I'm adding one more vertex, I need one more edge. But this gives size of vertex minus k plus k edges. Because remember, I had k edges in the cycle, but I don't have that many. But this is equal to size of v minus 1. So that's a contradiction. So if I'm connected and I have the right number of vertices and edges, then I'm also acyclic. And last but not least, D implies A. I already know I'm acyclic, and I have the right number of vertices and edges. I just need to prove that I'm connected. G is acyclic. So I just need to show that G is connected. If it's not, each connected component of G is a tree, right? If G is acyclic but not connected, then it's a forest. So each connected component is a tree. And then if I look at all of those trees, I know all of those trees have this relationship. Number of vertices is number of edges plus 1. And if I add all of those up, I'm getting a minus 1 for each component. So I get the number of vertices is equal to the number of edges minus the number of components. And so, therefore, the number of components equals 1, meaning G is connected. So G is connected and acyclic, and it's a tree. Okay, I will admit, I rushed through that proof a little bit. Don't normally do them that quickly. Still have 20 minutes, and there's a whole other topic I got to cover today to make sure you're ready for the quiz. But the key thing to take away are these equivalent conditions for a tree. being a tree is equivalent to having having a unique path between any pair of distinct vertices, which is equivalent to being connected and having this relationship, which is equivalent to being acyclic and having this relationship. And you can maybe read the proof more carefully another time. Okay, next thing I want to talk about is planar graphs. So a graph is planar if you can draw it without the edges crossing. So let me first define a planar drawing. This marker's dying. A planar drawing of a graph is a drawing in which no edges cross, except at vertices. So, for example, here is a planar drawing of this graph. This is planar. This is not a planar drawing. Same graph. But now I draw this edge and it crosses over another edge. And then a graph is planar if there exists a planar drawing. So what graph is this? What name do we have for that graph? It's one of our special graphs. K4, really good. So this shows that K4 is planar. Yeah, the complete graph on 4 vertices. K4, good. So K4 is a planar graph because I can draw it like this. I can also draw a K4 like this. This doesn't make K4 a non-planar graph. It just is not a planar drawing. Okay. And one of our important results about planar graphs is Euler's formula. So we had Eulerian graphs. This is the same Euler. If I look at a planar graph, I can not only talk about vertices and edges, but I can talk about faces. So faces are the regions enclosed by the graph. So this is a face, this is a face, this is a face, and then there's one more face in this picture. We think of it as the infinite face. It's the outside, it's the space outside the graph. So 1, 2, 3, 4. So if G is a planar graph with V vertices, E edges, and F faces, then V minus E plus F is equal to 2. Connected planar graph. Sorry about that. So let's look at this K4 example. I have 4 faces. I have 1, 2, 3, 4 vertices. Example K4. I have vertex is equal to 4. I have edges. I have 1, 2, 3, 4, 5, 6 edges. And I have f equal to 4. And indeed, 4 minus 6 plus 4 equals to 2. Okay, and you can do this any planar graph you like. Just start drawing vertices and edges. You're allowed to have cycles, that's fine. Just make sure your edges don't overlap. And make sure you are indeed connected. Okay, do that. And let's count everything up. So how many vertices? I have 1, 2, 3, 4, 5, 6, 7, 8 vertices. How many edges? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, looks like 12 edges. Nope, 13, missed one. And faces, I have 1, 2, 3, 4, 5, 6, plus the infinite face on the outside. And that's good that I counted my number of edges correctly, so I check 8 minus 13 plus 7 is indeed equal to 2. Okay. All right, so we learned, I think last time, that this is the class that prepares you to answer Facebook questions. That's the whole goal of this class. So let's do another one of those. You've got 3 houses. Wait, actually, I know I can draw this without lifting up my pen because it has an Eulerian trail, just not an Eulerian circuit. And you've got 3 utility companies. I don't know, gas and hydro and internet. And you have to, what you need to do is have lines run from each of the 3 companies to each of the 3 houses, and they can't overlap. So you want to draw 3 gas lines here, here, and here. And then you want 3 hydro lines, but they can't overlap. So maybe you've got this, and you get a little clever, and you go around, and you go around again. And now I'm going to run some internet lines, and I run that one, and I run this one, and then I want to get from internet to this house, but I can't. All right, I can't cross my hydro and my gas line. I can't come around and cross my hydro line over here. So this did not end up working. So good. So Jonathan's got the right idea. What am I trying to do? I'm basically trying to draw a K33 in a planar way? Right? Can I draw this graph without any crossings? So we only have 10 minutes left in class. So I will tell you two things. One, K33 is not planar. And two, you can solve this silly internet question because houses are not points. So you run this line under the house to get to the other one. And that's how you solve the silly internet question. You have to be able to go through a house or underneath a house. And it's not crossing, just running underneath. So that's the answer to the silly Facebook question. But K33 as a graph is not planar. And I'm not going to prove that to you. And I'm going to give you another non-planar graph. K5 is also not planar. And you're just going to have to trust me on those two. But I have good news, and then I have bad news. K33 and K5 are the only non-planar graphs. Okay. I've written something ridiculous, but I put only in red and in quotation marks, which is why I'm claiming it's okay to be ridiculous. Why is this clearly false? It's the best example to show it's clearly false. Yeah, K6. If K5 isn't planar, there's no way that adding another vertex and all of these extra edges is going to get me planar. Like, sure, I can add that one vertex in a planar way, but if I can't unravel this, if there's no way to make this one not planar, then how can this vertex help somehow? And that's true. So what I mean when I say K33 and K5 are the only quote unquote non-planar graphs is, if you are not planar, then you contain one of these as a subgraph. I'm going to write that down. So this is, scratch that out because that's not really true. Any non-planar graph except I'm lying to you again, contains K33 or K5 as a subgraph. Okay, so K33 and K5, I lied to you. They're not the only ones that are not planar. But if you have a non-planar graph, it's not planar because you can find one of these things. It contains it as a subgraph. That's why K6 isn't planar. It contains K55. Except I'm lying to you again. And it's obvious, really, I'm doing a terrible job of lying to you. Here's a graph that does not contain K55 as a subgraph. And it's not planar. And I think you'll all agree with me that it's not planar. See? It's not a K5, and it's got 6 vertices. These two guys aren't connected to each other. If I added in that edge, then it would contain K5 as a subgraph. That'd be fine. But look, it doesn't. There's no K5. But do you really think that like turning this edge into an edge with a vertex in the middle helped? Like it didn't help. Come on. You're being silly. So this is called a subdivision. Of K5. A subdivision of a graph is when you take an edge and you stick a vertex in the middle. So if I have any graph G, I have some stuff, and then I have an edge, and then I have some other stuff. I don't know. I got some vertices and edges going on in here, whatever's going on. And then I change that to the same exact picture, but I put a vertex in the middle of an edge. And I can keep doing that as many times as I want. This is a subdivision of G. And so here is the actual not lying to you result about planar graphs. It's not that K3 and K5 are the only ones that are not planar. And it's not that you have to contain exactly a K33 or a K5. It's these subdivisions that you have to worry about. So this is called Kuratowski's theorem. A graph is planar if and only if it does not contain a subgraph isomorphic to a subdivision of K5 or K33. So that's what we need to do to figure out if a graph is planar. Look at the subgraphs. We're not looking for a K5 or a K33 exactly, although those would be good enough. We're looking for a subdivision of a K5 or a K33. So if I drew something like this graph, that contains a subdivision of a K33. Right, and I can even add more vertices. Doesn't matter at this point. This key part means no matter what I do from now on, I'm not planar. Because that has my K33 with my edges. It just goes around that way. Oh, did I miss an edge? Yeah, I missed an edge. Sorry. Probably still wasn't planar, but now it's definitely not. With all the edges that I need to make my K33. Okay, I got 9:45. I will stop there. That should be everything you need for quiz 7, which we'll be releasing soon. Sorry that was a little bit fast. Maybe worthwhile to go back and watch this one again. But office hours today, as normal, 11:30 to 12:30. See anybody there that wants to talk more. Otherwise, have a lovely weekend. Enjoy some nicer weather, and I will see you next week.